Welcome grade 12s, and today we're going to do some chemistry revision, and specifically we're looking at chemical change, which means we're looking at rates of reaction, equilibrium, acids and bases. Redox doesn't come into this because that's part of your chemical that's part of electrochemistry. So it's really just rates, equilibrium, and acids and bases. I'm going to try to get through one question of each of those, okay? And we're going to do it in the order that you'll get it in your exam. So we're going to start with some rates, okay? So let's just go through the question. Now, I know that sometimes they're quite long questions. Don't worry about that. We're just trying to put it into context, and we'll get to the important stuff. So it says to us, the reaction between dilute hydrochloric acid, okay, and sodium thiosulfate, Na2S2O3, is used to investigate one of the factors that influences reaction rate. The balanced equation for the reaction is, and that should be arrow, is the sodium thiosulfate, don't worry about the -2 over there, plus the hydrochloric acid gives me sodium chloride, sulfur solid, water, and SO2 gas. The hydrochloric acid solution is added to the sodium thiosulfate in a flask. The flask is placed over a cross drawn on a sheet of white paper as shown in the diagram, and the time taken for the cross to become invisible is measured to determine the reaction rate. So there's the diagram of what happens. This is actually a really nice reaction, and if you've never seen it, and you have access to the internet, it's really worth Googling this and see if you can get a YouTube video of it. It's really nice to see. It's one of those reactions that will come up quite often because the reason why we do this is because by drawing the cross on the white piece of paper, when you add your solutions together, they go from clear to milky because you're producing sulfur, which is a precipitate, okay, and it doesn't dissolve in the water, and eventually you don't see the cross. So you can judge the rate of the reaction by how long it takes you to not see the cross. So you can judge it by the same amount every single time. It's a very easy way to get to the same place of completion, all right, or the same amount of product as you've had before because of not being able to see the cross. It's a really nice experiment. Now they tell you that you've got 4 experiments. A to D are conducted during this investigation. The volumes of reactants used in each of the four experiments and the time of the reactions are summarized in the table below. So we have the experiment, we have the volume of the sodium thiosulfate, the volume of water added to that volume, and the volume of hydrochloric acid, and then how long it takes for the reaction to take place. Then we've got a couple of questions, all right? So now these first 4 are fairly simple, so these are the first ones you're going to try. First, I want you to state the two factors that can influence the rates of the reaction. I want you to write down the name or formula of the product that causes the cross to become invisible. I want you to give a reason why water is added to the reaction mixtures in experiment B to D, and I want you to write down an investigative question for this reaction, okay? I'm not going to give you too long on these ones because we've got others that I think will take you longer and are a little bit more important for you. Well, that's a bad word. It's not that they're more important, I think they're just a little harder for you. So I'm only going to give you 2 minutes for these 4 questions, okay? So I'm going to give you 2 minutes, and your 2 minutes starts now. Okay, grade 12s, your time is up. I know you're not done, but that's okay. Let's see how you did, all right? So here, two factors that influence the rate of reaction for the rates of the reaction above. Now, the two easiest ones to do are, first of all, temperature. Now, they didn't change temperature on this one, but temperature absolutely plays a role. The next one is the concentration of the reactants. Please be specific here. Don't just write concentration, okay? Make sure that your examiner knows you mean the reactants. And the third one, and you only needed to write two, and those are the two I would normally write. The third one, yeah, it's a little bit out there, is you could add a catalyst. I would be hesitant to use a catalyst in a reaction like this because it doesn't need it. And also, I've never seen this reaction happen with a catalyst, but you could always put one in. We can't use pressure as one of the influences simply because we don't have any gases involved, okay? Then they asked you to write down the name or formula of the product that causes the cross to become invisible, and we would actually need to go back to the original equation to see that, and it's the sulfur, okay? So it's the sulfur that we need to do, so either you can write sulfur or you can write out sulfur, okay? Either way, it doesn't matter. Then, now this is quite important because now we're going to understanding the skill in the reaction. It says, give a reason why water is added to the reaction mixture in experiments B to D. What are we doing with the water? We're diluting we're changing the concentration. So why do we do it? To change the concentration. But we're changing the concentration of the sodium thiosulfate. Okay? And you can write it like that. The square brackets mean concentration, so we're fine, but it's to change the concentration of the sodium thiosulfate. It's to dilute it. Okay? That, of course, then brings us to the understanding of the next question, which is to write down the investigative question for this. This is so important. Number one, you cannot start these questions with the words will or does. Because if you start, will the concentration affect the rate of the reaction? You can answer that with a yes or a no. You'll get naught. Any question that can be answered with a yes or a no will get you naught, regardless of what you do. So we don't use, oh, no, that's not what I wanted. I wanted that. So we don't use will or does. Okay, let's just get rid of that silly little line. So there's lots of ways. So you're going to start, you can use the words how does, what is the relationship, what are they looking for in these questions? Do you recognize that there's a relationship between your variables? And secondly, do you know what the variables are? Now we're looking at reaction rate and concentration. So you could write a question like this, as an example, how does the concentration of the reactants, that's my independent variable, sorry, affect the rate of reaction, dependent variable. And it's a question, okay? So how does the concentration of the reactants, that's my independent variable, affect the rates of reaction, dependent variable, okay? I could have said, what is the relationship between the concentration of the reactants and the rate of reaction? I could have done, how is the rate of reaction affected when the concentration changes? Anything to that effect, okay? Nice and simple. Now we get to the fun questions. Now we have to actually work with the table. So now they say to us, in which experiment, A, B, C, or D, is the reaction rate the highest? So that's the first part. And use the collision theory to explain the difference in the reaction rate between experiments B and D. So I'm going to give you 2 minutes again. So you're now going to look at this, tell me which of these has the highest reaction rate, and then you're going to explain the difference in the reaction rate between B and D, okay? You are going to have 2 minutes, and your time starts now. So, grade 12s, let's see how we did. Okay, so now the question was, in which experiment A, B, C, or D is the reaction rate the highest? So you look at your times, and the one with the smallest time has the highest reaction rate. It means it went faster. So that means that's A. Brilliant. Now they say, use the collision theory to explain the difference in the reaction rate between experiments B and D. So now you look at B and D and you go, well, B happens faster than D. So now what's the difference? Well, it's not the HCl volume, but it is the concentration of the sodium thiosulfate. Because in D, we have 10 centimeters cubed of the sodium thiosulfate added to 15 centimeters cubed of water, whereas here I've got 20 and only 5 centimeters cubed of water. So B has a higher concentration. Okay, now whether you explain this answer from B's point of view or from D's point of view, it doesn't matter, just stick to it. So I'm going to do it from D's point of view. D has a lower concentration of D is lower than for B. Okay, so the concentration experiment B is lower. That means we have fewer particles per unit volume. Okay, that means there'll be less particles colliding with the correct orientation, okay? And or sufficient energy, because remember both of those need to be there, okay? Therefore, there's fewer effective collisions, and the reaction rate is lower. Okay, guys, collision theory means that you have to talk about correct orientation, sufficient energy, you have to talk about the collisions, and you need to talk about whether the collisions are effective or not. And it's all about the number of effective collisions. Remember, the greater number of effective collisions you have per unit time, oh, I must actually put that in, sorry. I think, oh, because that's one, so over here, I actually need to put in here, fewer effective collisions per unit time, because that speaks to rate for me, okay? Now, there is one more question to this part, but it's a little longer. So what I'm going to do is I'm going to let you take a little bit of a break, get your mind in line, okay with it, and make sure while you take your break that you find your periodic table, okay, because you can't do this question without your periodic table. So I'm going to give you a break, and when we come back, we're going to deal with the calculation, okay? So you're going to take a short break, and I'll see you in a couple of minutes. Welcome back. Grade 12. So now we're going to get to the section which I know you guys struggle with, but it's going to be asked. So now they tell you that the original Na2S2O3 solution was prepared by dissolving 62,5 grams of sodium thiosulfate crystals in dissolved water in a 250 centimeter cubed volumetric flask. Calculate the mass of sulfur that will be formed in experiment D. Now, what I'm going to do is I'm going to help you out here because you don't have the question in front of you. This is the reaction equation, okay, because you need this. So there we go. And because we don't want to have to keep referring to the table, what I want to remind you is that in experiment D, what we did is we took a volume, okay, so the volume of the Na2S2O3 that we used was 10 centimeters cubed, and the volume of water that we added to it was 15 centimeters cubed, because that's quite important, okay? So all the information that you need from the table and from the equation is there, okay? This one's probably going to take you a little longer. Hopefully you got your periodic tables out with you. It's 7 marks, Okay, so it's really, really, really important. And I'm going to give you 3 minutes, and your time starts now. Okay, grade 12s, how did we do? I'm hoping none of you gave up along the way, because this really isn't as bad as it looks, okay? Now, they said to us that we needed to calculate the mass of sulfur formed. The only way we can calculate the mass of the sulfur formed is to work out the number of moles of sulfur. The way we work out the number of moles is we look at the number of moles of the sodium thiosulfate that we used, okay? We need to start with this original information, okay? So where we start is we go, well, I know what mass we had, and I know the volume. So the first thing we're going to do is we're going to work out the concentration, the original concentration of the sodium thiosulfate. In order to do that, I need to know the molar mass of the sodium thiosulfate, okay? Now, that's why you needed your periodic table. Sodium is 23. Sulfur is 32, and oxygen is 16. Now, I've worked all of this out, so I'm not going to take the calculator out and do it because I've already got it. And this is 158, and this is just to save some time, grams per mole. Now I can work out the concentration of the sodium thiosulfate using that equation. And they told us that we had used 62,5 grams, and this is 158. Now, the original volume was 250 centimeters cubed. Remember, it's got to be in decimeters cubed, so we're going to divide by 1,000. And now this is 1,58 moles per decimeter cubed. Why is this important? Because I took that solution and I took 10 centimeters cubed of it. I added another 15 centimeters cubed of water to dilute it. But because I only took a small portion of it, I need to know how many moles of that solution I had. So the number of moles that I'm working with is concentration times volume. That concentration is 1,58. The volume of the solution, okay, is 0,01. I don't use the 15 centimeters of water, okay, because that doesn't change the number of moles. That just dilutes it. That changes the overall concentration. But I took of my original, I took 10 centimeters cubed. So actually, I'm working with, and it's a really horrible number, 0,0158 moles of sodium thiosulfate. Now, when I look at the sulfur to the sodium thiosulfate, it's a 1-to-1 relationship, and I have to show this ratio. Okay, so now I go here, and I go, fine, now I want the number of moles of sulfur, which is going to be this times 1/1, because that's the ratio that they're reacting. So I'm going to make 0,0158 moles of sulfur, but that wasn't what they wanted. They wanted the mass. So I take my number of moles and, I multiply by the molar mass of sulfur, which is 32, and I get 0,51 grams. Okay, nice and tiny, and I'm sure some of you went, oh, but Tracy, you make it look so easy, or you do it so quickly, but I've been doing this for a long time, so I shouldn't struggle with these. Shouldn't. Okay, now, let's move on to the next question. So here we go. Initially, 2,2 grams of pure CO2 gas is sealed in an empty 5 decimeter cube container at 900 degrees Celsius. Calculate the initial concentration. Not so bad. Give a reason why equilibrium will not be established. That's an interesting question. Because of the calculation, I'm going to give you 2 minutes, and you're going to answer those 2 questions for me, and your 2 minutes starts now. Okay, so let's see how you did. We've got to calculate the concentration of the CO2. Well, pretty much we can use the same equation we did just now, but I need to have, so this is 2.1, the molar mass of carbon dioxide. So carbon is 12, oxygen is, oh, that's not a 3, that should be a 2. So only 2 oxygens in carbon dioxide. So that's 2 times 16. That gives me 44 grams per mole. And they want concentration, and it's a 5 decimeter cubed container. So C equals M over M times V. So this was what, 2,2 divided by 44 times 5. Okay, and 0,01 moles per decimeter cubed. Now they ask an interesting question, because they say, give a reason why equilibrium will not be established. Well, all they put in was CO2. In order for equilibrium to happen, there needs to be a reaction taking place that has a forward and reverse reaction happening. There's no chemical reaction happening. Equilibrium cannot be established. Okay, simple as that. Now, we've done that. Okay, now they say to us, now calcium carbonate is added to the 2,2 grams of calcium, of carbon dioxide in the container. After a while, equilibrium is established. Well, now we have a chemical reaction. The equilibrium constant for this reaction at 900 degrees Celsius is 0,0108. Great. Now they say, give a reason why this reaction will only reach equilibrium in a sealed container. Well, this is a very simple answer, because there's CO2 gas being formed. If CO2 gas is formed, if it's not sealed, the gas is going to escape and equilibrium cannot be established. Okay? Now, calculate the minimum mass of the calcium carbonate solid that must be added to the container to achieve equilibrium. 7 marks. Okay, I know we've been going for a while, but I do want you to try this. So I'm going to give you 3 minutes, and your time's going to start now. Grade 12s, I'm pretty sure some of you are like, oh, it's Casey, I hate this. And some of you are trying really hard to use the table, and that's fine. You actually can use the table for this if you really wanted to. I like this question for a couple of reasons, but mainly because it's a little different to what you're used to. Also because they tell me what the equilibrium constant is, and I have solids involved. Okay, so let's look at what would happen here. Now, we want the minimum mass of the calcium carbonate. This actually is a normal stoichiometric calculation with one slight difference. Your Kc value, okay, the Kc expression is simply the concentration of the CO2 because those are solids. Now that expression happens to be equal to 0,0108. That means that the concentration of your carbon dioxide that we have in the equilibrium mixture at the end is 0,0108 moles per decimeter cubed, okay? From here, I can actually work out how many moles of carbon dioxide I used. Right at the beginning, in the first question, we worked out the concentration of, oh, no, we didn't work out the concentration. We can work out at the beginning. So initially, watch what I'm going to do here. Initially, the number of moles of carbon dioxide, mass over molar mass, is 2,2 divided by 44. So it's 0,05 moles. Okay? At equilibrium, the number of moles of carbon dioxide is going to be equal to the concentration times the volume. So that means that it's 0,0108 times 5, which gives me 0,054. Now, my carbon dioxide number of moles increased, which is what we expected because it's a product, okay? So the difference in the number of moles of carbon dioxide is equal to 0,054 minus 0,05, which gives me 0,004 moles, okay? That 0,04 must have been created from the calcium carbonate, okay? Because where else would it have come from? It's a one-to-one relationship. So the number of moles of calcium carbonate that we had to start off with must be 0,04. It's a one-to-one relationship, and we show that is 0,004 moles. Now, if I know that that's 0,04 moles, the mass is going to be the number of moles times the molar mass, which is 0,004, and calcium is 40, carbon is 12, oxygen is 16. That gives me 100, so we get 0,4 grams. Simple as that. You didn't need to use the Kc expression. It's more difficult to use the Kc table because you've got solids, okay? You don't have concentrations at the end. Makes life a little bit more difficult. This was the trick right there, okay? So I think it's time to give your brain a rest, so we're going to take a couple of minutes break, and then we'll be back. Got a little bit more to add to this, and then we're going to look at some acids and bases. So I'll see you in a couple of minutes. Okay, last section, guys, and let's just quickly look at a couple of extra questions. Now, same equilibrium system, and now they say to you, how will each of the following changes affect the amount of CO2 gas? The first thing is they ask you, write down increase, decreases, or remains the same, and remember this is at equilibrium, once it reaches equilibrium. If we add more calcium carbonate at 900 degrees Celsius, well, nothing's going to happen. It's going to remain the same because the equilibrium constant is the same, all right? It doesn't change the fact that we're going to get to a final concentration of 0,0108 because the equilibrium constant doesn't change because we didn't change temperature. Then they tell you that the pressure is increased. Well, here by changing the pressure absolutely affects the fact that you have a gas. Increase in the pressure means it's going to favor the side that has no gas particles, so it's going to decrease. Okay, so nice and simple. Now they ask you, okay, we've done that question, there we go. Now they say to you, it is found that the equilibrium constant at 727 degrees is now 2.6 times 10 to the minus 6. It gets lower. Is this reaction exothermic or endothermic? And they ask you to fully explain your answer now. Watch how we go through this. The Kc value decreased. Now, the only thing in the Kc value is a product concentration. That means the concentration of the products decreased. Therefore, the reverse reaction was favored. Okay? A decrease in temperature, which is what we did, all right, a decrease in temperature always favors the exothermic reaction. Which means for us, the reverse reaction is exothermic. So if the reverse reaction is exothermic, the forward reaction is endothermic. Question answered. Okay, work through it step by step. Look at what happens to the Kc value. Then, as a result, look at what happens to the products and the reactants. Then you can decide which reaction is favored and whether it's exothermic or endothermic. Okay? Let's go on to an acids-base question. This one's quite an easy one, this first part. It says hydrogen carbonate ions react with water according to the following balanced equation given to us. Define an acid, write down the formula of two acids in the equation, and then write down the formula of a substance in the reaction that can act as an amphiolite. This isn't actually that difficult, so you know what? I'm only going to give you a minute, and your time starts now. All right, grade 12s. I know some of you aren't finished. I'm sorry. I just want to get through quite a bit before the end of this lesson. So first thing it says, define an acid according to the Lowry-Bronsted theory. Well, an acid is a proton donor. Okay, nice and simple, not a problem. Write down the formula of the two acids in the equation above. So you go, which of these can donate protons? Well, HC3 is not going to, because watch what happens. The water is actually giving its proton, its hydrogen, to the HCO3 minus to create the carbonic acid, which then actually gives us away as to what those two are. So that means that the two acids are H to O, and the carbonic acid, that's nice and easy. Then they say, write down the formula of a substance in the reaction that can react as an amphiolite. Now remember, your amphiolites are substances that can act as both acids and bases, not in this reaction, okay? And this reaction is either going to act as either. In fact, there are two amphiolites, and the one I would expect you to write down without hesitation is water, but the second one is actually this molecule, is that ion, because it has the ability to both give and take hydrogens. Okay, they accepted both. Now, look at this. Look at this. Ooh. And we cry, it's all right. What I'm going to do is I'm going to work through these ones with you, just because we don't have enough time for me to let you work through them on your own. But that's okay. Now it says, during an experiment, 0.5 deciliters cubed of 0.1 mole solution of HCl is added to 0.8 mole deciliters cubed of a sodium hydrogen carbonate solution with a concentration of 0.25. They give you the balanced equation, and then they want to know the concentration of the hydroxide ions. This really isn't as difficult as it sounds. There's a trick to it though. So what we've got is they tell me that the concentration of the acid is 0.1 moles per decimeter cubed, and the volume of the acid that we use is 0.8. The base that we use has a concentration of 0.25, and no, I used the wrong volume, sorry. That volume is 0.1. Okay, so that's 0.1. The volume of the base that we use is 0.8. Now, in a situation like this, I know some of you attempted to go N over NB equals C over VA. You can't. The fact that they don't say they neutralize each other means that we have something left over. The fact that they're asking for the OH minus concentration means that I have to have base left over, and I need to know how much. So, first thing I'm going to work out is the number of moles of my acid, which is 0.1. Oh, wait, yes, hang on, wait. 0.1. I think I've written some of these equal, and yeah, 0.1, and that's 0.5. 0.1 times 0.5. So the acid, we have 0.05 moles of acid. Okay. The number of moles of my base that we're using is 0.25 times 0.8. Okay, and that gives me 0.2. Now you can see there's significantly more base. It's a one-to-one relationship between the acid and the base. So now watch. The number of moles of base that are used is going to be 0.05 times 1 over 1. Okay, so we want to know the number of moles of base left over, which is going to be 0.2 minus 0.05, which gives me 0.15. Why have I done that? Because if we go back to my original equation over here, which is this one, this shows me that when HCO3 minus breaks up, it gives me OH minus. This is just having the same, if I put an Na plus, I would end up with Na plus here. It's a one-to-one relationship, okay? So if I go back down here, I'm going to get a one-to-one relationship. So this number of moles tells me that the number of moles of OH minus is going to be equal to the number of moles of base that are left, which means I'm going to have 0.15 moles. But the question was, what is the concentration? So concentration is number of moles over volume. But now the trick is, what's the volume? Well, remember, in this equation, the volume of the acid I put in was 0.5. The volume of the base that I put in was 0.8. So my total volume is 1.3. So that gives me 0.12 moles per decimeter cubed. Sure, I went through that very quickly. I'm sorry, because I want to get to the last question. This is really important. That's the look, it's a shoe. Concentration of the OH minus. Why is that important? Because next question, what's the pH of the solution? Okay, I'm so going to run out of time. Watch here. OH minus times H3O plus gives me 1 times 10 to the minus 14. I know that that's 0.12. That is what I'm looking for. Okay, now I divide by the 0.12, okay, which I have worked out already. Give me a second while you work it out before you come. So we get 8.3 times 10 to the minus 14. And I know some of you are going, but where are you going with this, Tracy? Well, remember, to get pH, I need the negative log of the H3O plus ion. Okay, so now I go negative and I just type this into my calculator. Okay, and I get 13,08, and I'm happy with that because I have OH minus ions left over. That tells me that my final solution will be basic, quite strongly basic. Okay, but I'm actually going to end up with, in my final solution, NaOH. I end up making sodium hydroxide. That's an incredibly strong base. I expect a high pH there. Okay, I went very, very quickly. Now, if you got this OH minus value wrong, don't worry about it. If you use it correctly like I've done in this question, you'll still get all the marks for that. Okay, guys, remember this section is practice, 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 and I've run out of time, so I need to say goodbye, and I'll see you again next time.
Matrix 2021 Catch-Up is brought to you by the Department of Basic Education, NECT, ETDP-SETA, SABC, MultiChoice, and DBE TV on OpenView Channel 122 in partnership with